2, for example, we have already finished practical, right, today at noon. Okay, so I just put a checking point for those if you need more help about the code. You can run this, download this on your own personal machine, and then run it to see how our tutor solve each question here. And also for tutorial, for example, on Wednesday, this Wednesday, Agi and Mano has already finished all tutorial sessions for Unit 2. So on Wednesday, I have already put solutions for tutorial 2 online so that you can check your answer now. Okay, we still have joiners here. Let's start, otherwise we cannot finish on time. That is how we would like to spend our time today. Okay, so 15 minutes for limits, and then about 15 to 20 minutes for derivative and differentiation. Some rules you need to apply for. And you also need to learn chain rule. Finally, we will have about 10 minutes to have a look how these calculus can be done in a Jupyter notebook. Now, I'm going to record
Recording in
session.
Progress.
Calculus. On Tuesday, we have already learned functions. We focus on one single variable. And although we also mentioned 2 at the end. So today, for this session, what do you need to know at the end of this session? You should know how to use limit definition to find the derivative of function. Okay, how to calculate derivative by applying rules of differentiations and some, again, similar rules. So here, please distinguish 2 things. In the past 2 semesters, we asked students in the final test to calculate derivative. You need to look the question carefully. Sometimes we ask you to calculate derivative based on the limit definition. Sometimes we ask you to calculate derivative based on the rules. So when you are giving a test question, please pay attention which one you have been asked to do. Many students found, okay, when they learn mathematics, they need to know how they can use and where they can use what they have learned. So because we have very short time for each lecture here, I cannot have a look at watch those videos with you together. But after this session, I hope you have some time to have a look at how people actually use derivative and an integral to solve real-life problems. The videos are not very long, especially this one, the last one, only 3 minutes about, and the other 2, each of them is about 10 minutes. For us, all of you, today after we learn derivative, and next week you learn a little bit more derivative and also integral, then we will apply what you learned here for finding maximum value and the minimum value for an objective function. That is what we are aiming for. Some of you have already registered on machine learning and neural networks. In that module, you will then see deep learning and traditional neural networks. There, you must know activation functions and the derivatives. Okay, so the calculus is widely used everywhere. Let's start with limits. Here is an example. It says when x approaches 1, function fx is defined here. Fx is equal to 3x. Then function is here approaches to 3. Okay, then x start from 0, approaches to 1. Function defined by 3x goes from 0 to about 3. To say this is too long. We can just use one single short equation to express the whole statement here. So this means here the limit when x approaches 1, function here approaches to 3. Why do we need limits? Let's have a look at the example here. Some functions are not defined at a point but are well behaved nearby. For example, here, this function. This function expression is given here. Okay. When x equal to 2, the function is undefined. Why is that? Because when x equal to 2, here, the denominator is equal to 0. When something is divided by 0, it's called undefined, not equal to 0. Okay, the whole thing is not equal to 0. It is undefined. However, although when x equal to 2, this is undefined, if we see x approaches to 2, the function defined here, right, approaches to 4. Approaches to 4. So the limit when x approaches to 2, the function's limit is 4. This means here, when x is near 2, but not equal to 2, the value of this function is near to 4. So how near? As near as your heart desires. Okay, so let's have a look at here. Let me ask you. That is the function we have just already seen. Okay, how did we calculate the limit? We actually applied difference of two squares. Okay, so here we expand here using x minus 2 multiplied by x plus 2. And then we can cancel x minus 2 in numerator and denominator. This gives us 4. Now, since fx is defined here, can be written like this, and then we can cancel this x minus 2, right, from numerator and the denominator. It gives us x plus 2. Can I say fx, which is defined here, is equal to gx? We can't. We almost can, but actually they are different. Why is that? Here, remember Tuesday we talked about function. We talked about a function domain and range. What is domain? Domain is the set of all possible x values which will make the function work and will output real y values. For this one, domain x can be any real numbers. But for this one, domain x cannot be equal to 2. When x equal to 2, the function is undefined. So we almost can say they two are equal, but actually, just because this x equal to 2 issue, they are not the same. Left limits and right limits. Let's consider x and x0 as points on the real axis, where x0 is fixed. What I mean is here. We have real axis, and we have a fixed x0 on this real number line, and x approaches x0 from left. Then what we can write, we write it like this. X approaches x0 from left. On the other hand, when we have a x value, we move x from right to x0, then we can write it down like this. This means x approaches x0 from right. Yeah, similar like here, x0 now is 3. 3 is our x0. X can approach 3 from left, then the limit of this function is equal to -1. When x approaches 3 from right, the function here in this part is a constant, which is 1. So the limit for this part is equal to 1. In this example, two-sided limits are not the same. They are not equal. Okay, one is -1, the other one is 1. So limit definition summary. Here, the whole thing here is called the left-hand limit of f at a. This one here is called the right-hand limit of this function at a. Okay, one is from left, one is from right. When two-sided limits from right and from left are equal, then we have the limit for this function at that point equal to L. Then we can say here. Okay, that is, if we have this, then that means the limit, two-sided limits, they are equal. So, another thing after this limit, let's have a look at the continuity. F is a function and is defined for all values of x near a fixed value x0. Okay, so f is a function, has a defined value for x equal to x0. This function is called continuous if at this fixed point, the function's value is equal to the limit of this function at this point. So here, I give an example, but I prepared another example. Maybe it's better to understand this. Have a look at, I have 4 diagrams here. Which one is a continuous function? Which one are not? Let's have a look at diagram A here. The left and the right-hand side limits are not the same at x equal to x1. So the two-sided limit doesn't exist there. Therefore, the function isn't continuous at this point. Okay, so I make it maybe clearer here. From this sentence here, it actually includes 3 things, requires 3 things. First, the two-sided limit exists and is finite. Second, the function at x0 is defined. You see, it's defined. We have, a function is defined at x0. Number 3, the third one, 2 quantities. 2 quantities are equal. That is here. So back to here, we say this one is not continuous because two-sided limits, they are not equal. Now have a look at here. Diagram B. The left and right-hand limits exist and are finite and are equal to each other. Okay, it's here. So the two-sided limit exists. However, the function is not even defined because here there's a gap. So this is not continuous function. What about this one? In diagram C, the two-sided limit again exists, right? When x move to x1 from left and from right, the limit is there. And the function is defined. That is this solid point here is defined. However, this one doesn't equal to the limits, the two-sided limit. So that's why the function is not continuous. Finally, for diagram D, since the two-sided limit at this point exists, and the function at this point exists, and the two quantities are equal, so this is continuous. Now example. How do we calculate very simple limit for a function? For example, here, the function is defined very similar to the previous one. It's defined as shown here. To calculate the limit, when we notice that when x equal to 3, the function is undefined because here denominator equal to 0. However, we can do some changes to this function. That is, we use the difference of two squares and rewrite this part. That is what we get. Cancel this term from numerator and the denominator. That is what we get. That is the limit. Now, I hope you have a pen and a notebook. Write down what is your answer for this exercise here. What is your answer? Lovely. That's great. Thank you. So, have a look at here for those if you have not done it. That is how you do it. The function is defined. Oh, I did a mistake. Okay, here I should have lim limit. Okay, function is defined here. Let me make it correctly. So what I mean is here should have. Okay, now it is correct. So that is 1/4. It's great to see many of you have already done it correctly. Now, have a look at next slide here. How do we define the slope for this secant line? We define it using the change in fx. Here is fx. Here is along the x-axis the change in fx over change along this x-axis. Okay, so this is the slope. If this line becomes smaller and smaller, I mean, I push this line to here, and it becomes to here and here, then eventually it is the tangent at a specific point on this curve. Okay. So what is derivative? Derivative for a function, for given a function, okay? The derivative is the slope of the tangent line to the curve at a specific point, x0. It is defined, this is the derivative of this function is equal to the limit, that is when the change along, just think about that graph, the change along the x-axis approaches 0. And what is the change in the function? If we go back to this graph here, as we can see, the slope of the tangent line depends on which value of x we start with, right? So I may have slope here, I may have slope here. Another way of seeing this is that the slope of the tangent line through a particular point, say x and fx, this point, every point along this curve is defined by two values. One is x value, one is fx value. So what I'm saying is, another way to see that is that the slope of the tangent line through a specific point is itself a function of x. So the derivative is a function of x. Now, let's have a look at here. Example. In this example, remember on the very beginning when we talk about learning outcomes, I said in the test, quite often you are asked to calculate derivative, but you need to be careful how we ask you, which way you need to do, by definition or by some rules. So here we ask you to use the limit definition, find the derivative of the function. Here the function is defined by this. And what is the solution? Solution is using the definition of the derivative